Yeah, so here I solve two ODE examples. Each one I try to show you some little technique. Okay, all right. The first one I like to show you this one. Nope, not that. No, because that quite annoying. All right. Find the general solution y prime equals ay plus by squared. Yeah. A not 0, b not 0. A, b constant, but both not 0. Yeah. Yeah. It's not very hard, and we know, in general, we know how to solve it because it's separable, right? Yeah. But when you solve, there is some small technique you need to apply. Yeah, so here I want to talk about that technique. Yeah. All right. Now, first, by the separable method, we can write it in this way. Yeah. Very easy. So we can write the integral like this. Yeah. But the question is how to calculate the left-hand side integral. Yeah. We did one example last time. Yeah. Remember last time? Last time we talked about partial fraction technique, right? Here, the situation we need to apply partial fraction technique. But here I want to show you a special method. We do not have to go through the standard computation procedure of partial fraction. We have some shortcut, faster way to calculate this integral. Okay, let me show you that way. Yeah. How to calculate the integral in this form, the ay plus by squared, you can see we can do factorization on the denominator. Two factors. Yeah. We can factor y out. Yeah. So that's simple factorization. Yeah. Before we do that, yeah, because AB constant, a little, annoying, not quite convenient. Yeah. We want to make the formula more friendly for our calculation. So here, how to make more friendly, this step, I factor that b, leading coefficient. Yeah. Y squared term, leading coefficient of the denominator is b. So after I factor this b out, the leading coefficient becomes 1. That's more convenient. Yeah. Usually we want to make a leading coefficient 1. So in computation, that would be relatively easier. So we do that step, simple step. Okay? We factor that 1 over b out of the integral. Then the denominator function, yeah, so this is a situation of partial fraction technique, standard situation for partial fraction technique. Yeah. But when you work on it, usually you need to do a lot of calculation, right? Yeah. A lot of calculation. Yeah. You can practice that. Okay? Yeah. But here I like to, because the structure relatively simple, we can do it a little faster without going through that standard process. Yeah. All right. So let's write this fraction as sum of two simpler fractions. The goal of partial fraction, we write one relatively harder fraction form as sum of two simpler fractions. That's our goal, right? When we do that here, let's do factorization, factor y out. Yeah. Then we have the product of two linear functions of y. Two linear functions of y. Yeah. And each linear function, the leading coefficient is 1. leading coefficient is 1. Because in that way, our calculation would be easier. Make a leading coefficient 1. Yeah. Now, let me split. Now we can split this fraction in this way. I show you here. Here, I split this more general. So this is a general form of that. More general, okay? Product of two linear functions. Each linear function has leading coefficient 1. Okay, the product. Now I show you how to split this fraction into sum of two simpler fractions. Yeah. Split in this way. Yeah. Let me explain how to see that. All right. Yeah. First, let's ignore this constant part. Okay, I cover it. First, let's use 1 over the first linear function minus 1 over second linear function. Yeah. First, let's take that. When you take that, you do common denominator, numerator x plus b minus x plus a, x cancel out. So the numerator becomes b minus a, but you want to make the numerator b. So you divide b minus a here as the constant part in front of the parenthesis to make it a 1, okay? Or to make it both sides balanced, all right? So you do that, all right? So you make, difference of two simpler fractions. Yeah. The denominator the same, both sides, but numerator is different. Numerator becomes b minus a, okay? I hope you can see it. Yeah. Common denominator, so x plus b here, x plus a here, difference. X cancel out, b minus a. B minus a, how to remove the b minus a? You do division, 1 over b minus a to cancel it out. Yeah. So that's the way we split. Yeah. Try to get used to it, okay? Yeah. Try to, feel comfortable, yeah. Understand in this way, this split. Because if you do this way, you don't need to do partial fraction, right? You get around the partial fraction. You have a, you have b, you need to set up two equations, solving for a, solving for b, right? That's the partial fraction way. Here we do not do that, a and b. We do the split, and we get it immediately, all right? Yeah. So I recommend this method to you, all right? Now let's do this, okay? Yeah. So let's write the parenthesis part, 1 over y minus 1 over the second linear function, okay? Yeah. But we need to fix this constant and adjustment part, right? Because the numerator, if you do, common denominator, numerator, a over b. So you need to divide this a over b, so you times b over a. You multiply reciprocal of a over b. That's b over a. After you do this multiplication, you make the numerator 1, okay? So you can check, yeah, both sides the same. Yeah. That's the split, okay? That's the split we need. Yeah. All right. Now, we do the integral calculation. Yeah. All right, so this one equals, yeah, because you have cancellation. This 1 over b, this b over a, b cancel out. 1 over a, the first integral, 1 over a, the second integral. Okay? Yeah. 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 Practice a little bit. Yeah. Then you can do better. Yeah. Yeah. So you write natural log like that. Yeah. So let me show you how to write out the whole solution. Like, whole general solution. Yeah. All right. Then, yeah, so one side, this right-hand side, yeah, because 1 over a, you multiply a both sides, so you get ax plus a times c star. Yeah. Yeah. Then remove the natural log, And absolute value, we also want to remove absolute value. So we put a plus minus sign. Okay, this E term. It looks familiar, this part. How do we handle it? This part. C. Yeah. Good. So the second time, you can do better. Yeah. So let's just replace that big chunk by this little c. All right? Yeah. Yeah. Okay? It looks much better, but we need to solve for y. We need to write y expression. Yeah. Both sides you have y, but we need to solve for y. Okay? The y expression we can write in the first time we write this way. Yeah. But you can do some further. Yeah, here. Yeah. Look at that. Yeah. One special way we simplified. We want to do division, both numerator, denominator by this numerator. Because numerator, when we do division, it becomes 1. Okay? A lot of cancellation here, and the remaining part. Yeah. But when you do division of the numerator, C could be any constant, right? C could be any constant. But if C equals 0, can you do division? You cannot do division. If C is 0, how can you do division? Yeah. All right. But if C is 0, your y equals 0, it is the one special solution of the equation, right? Yeah. Y equals 0, it's a special solution. Let's take it out. Right? We know that y equals 0 is a solution. So we, put it aside. Then we consider the remaining cases. Then we do not allow C be 0. Okay? After we take y equals 0 solution aside, we can assume C cannot be 0. Then we can do division. How about that? Okay? How about that? Yeah. So after we do the division, 1 over, because this C part gone, B over A, that part, so here, another thing, all right. B do division over that. Oh, sorry. Yeah, B do division. Yeah, so look, here. Can you see something strange? Can you see something strange? Not quite balanced. Right? Yeah. Because, all right, the numerator, no problem, right? We do division by this numerator term. Numerator is 1. That's easy. Right. This term is okay, right? We use this term divided by the numerator, we get a B over A. That's okay, right? Now the problem is the first term. The first term, B over that. Okay? B over that. Yeah. So let me write it on the screen. B over that. Okay? All right. So it should be this part after the division. It should be B over AC times e to the negative ax, right? Can you see this after division? It should be like that, right? All right. No problem. No problem. This part is fine. But a b over ac, can we treat as a new constant? C is arbitrary constant, right? Arbitrary non-zero constant. C is arbitrary non-zero constant, right? Yeah? C is arbitrary non-zero constant. So B over AC is another arbitrary constant, right? Another arbitrary constant. Can we use a constant symbol represent that whole thing? B over AC. Let's say C1. Is that okay? We can use C1, right? So if I use C1 here, you have no problem, right? Yeah. But if I use C, do you have a problem? If I use C, do you feel okay? Some of you feel okay. Some of you feel not okay. Yeah, right. Yeah, it's true. Yeah. Both of you correct. Both of you correct. So in math, we have situations we can do this way. It's okay. It's okay. Why? We abuse the notation. Okay? Here we abuse the notation. Although we can introduce a new C1 notation, because that would make us use too many notations. So sometimes mathematicians, in this situation, they just use the older notation, they abuse it. Okay? Abuse it, but that would not cause problem. Because we just need a constant there anyway. Whatever constant it is. We just need a constant, non-zero constant. Okay? In this situation, we abuse the notation. All right? Yeah. The purpose, we do not introduce a new symbol. We use our old symbol. But the result is fine, right? Result has no problem. Think about, let's use C1 first. Okay? That's our result. When you copy to a different location, can you change C1 back to C? Yeah. When you copy the formula, it's not here. You copy your formula to a different place. Can you change the C1 back to C? No problem, right? Yeah. So that's the reason. Even if we abuse the notation, there is no problem. Yeah. We're fine. Yeah. So that's, quite common in math formula manipulations. Yeah. All right, just let you know. Yeah. All right. It's not wrong. Yeah. All right. C, but C cannot be 0. Because B not 0, A not 0, C not 0. How can this fraction be 0? Cannot. Yeah. So this C cannot be 0. That's our general solution. Okay? That's our general solution. Yeah. Then, let's review singular solution another time. Singular solution. Refresh your memory. Y equals 1 is a solution. Can you see y equals 0? Can you see y0 is just a singular solution of this equation? Can you see that? What's the singular solution? Again, yeah, let me ask you this question again. Before the break, we saw singular solution, right? We just reviewed. Not obtainable from the general solution, right? Yeah. Look at, this is our general solution. Can you obtain y equals 0 from this general solution expression? You cannot, right? Because this expression, it can never be 0. 1 over some number. How can you make 1 over some number be 0? You cannot, right? 1 over any number, you cannot get a 0. Any specific number. Not infinity. Don't tell me you put infinity at the denominator to get a 0. Because infinity, you can only, when you consider limit, you can use infinity, right? If you consider concrete number, how can you treat a concrete number as infinity? Right? Only when you take a limit, you can put an infinity there. The limit of a sequence is infinity. You can say in that way. But for a concrete number, just a number there, whatever it is, you put there. The whole fraction is not 0. So you can see it's a singular solution. Singular solution. This example. You see, concrete example. How we get a singular solution. Yeah. All right. Any question? Yeah. So that's the whole example. Okay? Yeah.
On the right side under partial fraction technique, did you do partial fractions to get to the b over a parentheses 1 over y minus?
Here I didn't do partial fraction. I get around it. Okay? So here just basic algebra, the manipulation. I avoid. Yeah. Partial fraction is if I do it in this way, then you can see it's partial fraction. If I do, certain fraction is capital A over y plus capital B over, y plus something. Yeah. If I do this, that's a partial fraction way. Okay? Then we need to determine capital A, capital B. Okay? Yeah? So usually you need to do a lot of calculation. Yeah. Here I want to introduce a shortcut, easier way. If you can understand, if you can, practice, get yourself learn this method, then, think about in the test. So you're doing here. It can save you about 5 minutes, right? Think about that. Save you 5 minutes. If you practice, some faster methods, save you a lot of time. Okay? Yeah, try to practice. First, understand. Yeah. I understand this method. Then practice.
At the end, you said this solution was singular, but it's not singular, right?
This one is singular. Y equals 0.
Why is it singular, but the general solution?
No. General solution, all the solutions that are covered by general solutions is not singular. Or are not singular. Yeah. Singular, completely different from, the huge group, right? Yeah. Singular, single out. Yeah. All right. Next question. This one, number 2. Yeah. Actually, I passed the 20 minutes already. Yeah. Let me finish it. Yeah. Let me finish it. Okay. The remaining, the part B, I have 2 slides. So if I cannot, I leave it to next time. I have 2 slides. All right. Solve this equation. Are you familiar with this equation a little bit? Saw somewhere? Anyone remember? Yeah, homework. Good. Homework. Yeah. So that question, we remember Newton's law of cooling. When we apply Newton's law of cooling, the room temperature in the example I gave you in in class, we use constant outside temperature, right? Do you remember? Constant outside temperature. 50 degree, 40 degree, we take average outside. Then that homework question, I change it. We use a linear function to represent outside temperature because it's not a constant. Okay? It changes from 40 degree to 50 degree. So we want to draw a line, connect these 2 points. Then we write the function, represent that straight line. Yeah. After we represent a straight line, we get this is the function. Okay? This is the linear function connecting the temperature, outside temperature, from 10 p.m. to 6 a.m. Yeah, those 2 points. Okay? All right. Now I want to, in the that exercise solutions, I ask you a question. Can you solve it? Yeah. I didn't solve it. Here I just solve it. Okay? As a practice question. Let me solve it. Yeah. But I found it looks like not hard, but when I solve it, it took me a lot of time. Yes. Yes. I got stuck at one particular place. Yeah, I'll show you. Yeah. One particular, yeah, but finally I fix it. Yeah. All right. First, I write it to, because T, capital T, little t, we're not familiar with the symbols. So I switch to YX. Yeah. Our usual familiar symbols, XY. Okay? So we get this form. Then let's write standard differential form. Yeah. dx dy. Standard form. Okay? Yeah. So we just, copy the, the process, the steps of that process here. Yeah. Yeah. Calculate these 2 fractions. Yeah. Yeah. If r equals the first fraction is a variable of x, then we can calculate integrating factor f of x in this formula, right? The second option, r star this fraction, if it is a variable of y, then we calculate the integrating factor f of y using this formula. Yeah. That's what I copied from part C. Okay, module 1 part C. Yeah. Yeah. Put it aside. Yeah. So we can do it. Yeah. We can calculate integrating factor here. All right. Do the calculation. First, let's calculate R. Okay. Partial derivative, partial p over partial y, it's just the k. Yeah, because this big thing will only have the first term about y. Okay. Yeah, just k partial p. But second one, q is -1, partial q partial x. That's 0. Okay. So the second term is gone, 0. Denominator -1, so r equals negative k constant, some constant. So our function very simple. See, we do not need to go to the next one because it's already the simplest case. Why we need to look at further? Although you can try, yeah, but here to save time, I just use r to calculate f function. Yeah. Integrating factor f equals e to the negative kx. Yeah. So we have the integrating factor. Then let's just multiply integrating factor to get this new differential form after we multiply integrating factor. Okay. Then we do integral two integrals, u function, uxy function. The first one, integral of m function, this whole m function, okay, plus k of y function. Yeah. Here, k there, k, yeah, you're confused, yeah, but we know what it is, okay, yeah, we know what it is. Yeah, do not get confused. Yeah. All right. Then, here, the integral of m function to get this one, this is the place that took me a lot of time. Okay? The integral of m function to get this one, because in it we need to use a technique called integration by parts. Do you still remember integration by parts technique? Yes. So here, so when you do this part, okay, this term multiply that integration by parts. Okay? The first, second term you do not need. Or you treat the whole thing, integration by parts. Yeah. Yeah. It took me, 1 or 2 hours, that long. Yeah. 1 or 2 hours. Always wrong, always wrong. Okay? Yeah. Yeah, because I take derivative. Always, no matching. Yeah. Okay? Yeah. Anyway, yeah. Yeah. But here, do you want me to do it here, right here, integration by parts, or do you want to practice yourself first? If you cannot make it, then I will do it for you. Yeah. Yeah. You can try. You can try. Yeah. Here, because here I tell you this is the answer, and you do integral on this m function and see if you can get the same thing. Yeah. Just remember you need to do integration by parts. Yeah. If you cannot do it, yeah, so I will find some time to do it for you. Okay? Or I just, I just modify my solution file, add this part. Then I do not need to do it in class. Okay? I just add this computation details in the next version. Yeah. All right? So then I can save some time here. Yeah. Otherwise, if I finish that, the whole class is gone. Yeah. The whole class is gone. Yeah. All right. Final solution. Yeah. Because the second part is easy. Second part for m function, that m function is so simple. m function, just one term, yeah, plus L Remember, when we have two expressions for the same u function, we can write the final u function immediately. Remember, I mentioned that many times. We just copy the common terms. Not common term, union of the terms. Not keep the common term, keep one copy of the common term. Okay? The union of the terms. Yeah. Here the union, yeah. After that, because there is a c, so I multiply that c, I can get a y equals this expression. There is a c here. Okay? So that's the final solution, c here. Okay? Yeah. I plug in, I check, I plug in into the original equation, it's correct. Okay? Because if you want to check, you need to go back to the original equation and see if both sides match. Both sides match. Yeah. 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 Originally it looks simpler, looks very simple, right? At the beginning, this equation looks not complicated. Yeah. But when you do it, you can see it's not that simple. Okay? Yeah. It's not that simple. All right? Yeah. 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 Try to study, understand this. Yeah. Because I can modify this question to give you in either homework assignment or tests. I just, make the story because the room temperature, right? Outside, inside, that thing. Yeah. Okay? Yeah. Oh, another thing I'm thinking about. It's a 2-hour class, right? Yeah. That means your test also 2 hours. Okay? So you sit here, whole 2 hours. Do you think you use 2 hours, you can do, I plan to give you 20 questions. Yeah. Although 20 questions, but not, many concept questions, right? About one half concept questions. True or false, multiple choice. You don't need to do calculation. Okay? Yeah, one half. The other half, you need to do some calculation. Yeah. But not brand new questions.
Are the integrals going to be as difficult as those?
Usually not. Yeah. Yeah, but here I give you, and we will practice a few times. So if it's a brand new one, then probably, that's something I also want to ask. Yeah. All right. Because solving word problems, you feel relatively hard, right? Solving wording problems. Yeah. So if 2 hours, you may not feel enough solving word problems, right? Yeah, because we may have several word problems. Yeah. You need to spend time to understand. Yeah. So I may consider a way, for your test. Yeah. I move 5 word problems online, out of class. So when you sit in class, so we reduce. We may solve 1 or 2 word problems, but not too many. Okay, yeah. So computation and 1 or 2 word problems, but for the 5 word problems, you have several days to complete it. How about that? 3 or 4 days to complete it. Yeah. That's something I can give you more time for the test. Midterm, final, both in this way. Yeah. Do 5 word problems, you have plenty of time. Yeah, but definitely, it use your free time, right? Your spare time. Yeah. Yeah, that's my plan. Yeah. Otherwise, it could be very hard, right? Yeah. All right. Let me continue. Yeah. Yeah. Now, I want to explain one of the homework questions. I want to explain that because one student asked me, one student sent me an email, asked me, understanding. So you can tell me. So if you have tried it or not. Yeah. I just want to give you some hint here. Yeah. Have you seen this question? Number 20, part B. Yeah. A thermometer reading 5 degree centigrade is brought into a room whose temperature is 22 degrees C. 1 minute later, the thermometer reading is 12 degrees C. How long does it take until the reading is practically 22 degrees, say 21.9 degrees? Try a little bit and tell me what do you feel about it? How do you? We know we need to use Newton's law of cooling, right? Yeah, everyone knows that. But how to use it? Do you have a, confidence way to work on it? That student showed me, his understanding. Yeah. I saw some problem. So that's the reason I want to explain today here. Let me use the final 10 minutes to explain. Get it right. Yeah. But I only give you a hint. You need to find the solution. I cannot solve it for you. Yeah. All right. It relies on your understanding of Newton's law of cooling. You know its content, right? Newton's law, I do not need to repeat. You know its content, right? Yeah. All right. So here, we need to apply in the right way. Yeah. So, Newton's law of cooling. Yeah. But here I emphasize the understanding, importance. When you solve a word problem, especially word problem, your overall understanding should be very good. Otherwise, it's very easy, so you get the wrong way. Yeah. Because most of the students, so when you apply the formula, Newton's law of cooling, you just take the form, okay? Because you have old formula, you just do some analogy. This number corresponds to this one, that corresponds to that one. I just make one-to-one correspondence without understanding. Yeah, because that understanding pretty shaky. Yeah, not solid. Okay. Yeah. Here I want to fix that understanding part. Yeah. So the situation of Newton's law of cooling. Let's recall our original question. We applied Newton's law of cooling. We have an office, right? We have a room. So this room is office. Yeah. So that air conditioning, keep the room temperature, down. Then around the office, that's the outside environment, right? Yeah. Outside, But that's outside. We treat as environment, right? Okay. So outside temperature, basically it's the environment temperature. How about that? Okay? Yeah. So we have some small area. Office is a small area, right? Yeah. Small area, its temperature has some significant difference with its outside environment temperature, right? That's the situation. Then, Newton's law of cooling, the outside environment, when we say environment, something big we can call environment, right? Something small, can you call environment? We do not call. So, some ice box, whatever, some small box. That not large enough, we can treat as environment. Outside, okay, open air, that's the environment. So the environment brings down the room temperature, right? Oh, cooling, that brings down. Outside temperature colder than the room temperature. Room temperature higher. So outside temperature brings room temperature down, closer and closer to the outside temperature. So we set up equation, Newton's law of cooling. Outside environment makes the room temperature cooling, right? That's the understanding. All right. Yeah. Now we get to this question. This question, what's the situation? Okay. All right. This question, we have an environment, okay, this time. So what's that environment? Okay. We bring a thermometer from outside inside, okay? So thermometer, so here, yeah. It's a, object, yeah, let's say, so this is thermometer, okay? Yeah, so we bring it from outside into the room, okay? All right. So this is the room. All right? Now, based on your understanding, what is the environment? What is the environment? Can we treat thermometer as the environment? Thermometer. One little object. Okay? And from the context of the question, the room temperature brings the thermometer temperature up, right? Up. Now the thermometer temperature brings the room temperature down, right? Because room temperature basically no change. So what is the environment? Yes, room is the environment. Okay? The previous one, office. Office is not an environment. Because you compare with outside world, office is very little. Because the office temperature, office air conditioner, you cannot bring outside temperature down, right? Outside temperature, your impact is so little, can be ignored. Here, your thermometer, you cannot bring the room temperature up or down, whatever, yeah? Yeah. Only room temperature can bring up your thermometer. Okay? Yeah. Now, when you apply Newton's law, you set room temperature as TA. Is our TA? Our TA is the environment temperature, right? TA is environment temperature. And this TA is higher than the thermometer temperature, right? Thermometer initially 5 degrees. Then going up 12 degrees. And finally 21.9 degrees, close to room temperature. Okay? So here we can say, actually we modify original Newton's law of cooling as Newton's law of heating. Because you heat up the thermometer. How about that? You heat up so here we change this, the version here, we do the heating. Not cooling. Okay? Yeah? But your equation format similar. Direction opposite. You heat up. Okay? That one cooling, going down. Okay? Here, going up. The temperature T function going up. The cooling one, the temperature function going down. Okay? The opposite. Can you use this new understanding to set up equation and solve it? Okay? Yeah. So this understanding is important. Okay? Yeah. Do not just copy the old equation, try to replace some numbers. Yeah. That may not be good. Yeah. So understanding is important. Analysis. You need to do some analysis like this. Okay? Yeah. All right. Yeah. That's it. Yeah.